Alright, now we'll start our first discussion of fluid mechanics. And in this discussion, or in this video, we will discuss the overview of the fluid mechanics. And we have to define what is a fluid and how does it differ from solids. And then the last part of this video lecture will be discussing the different fluid properties. Okay, so fluid mechanics. Now you have already learned or studied the meaning of mechanics, or the description of mechanics. And when we say mechanics, it just means that it refers to the forces and body's response due to the applied force. Okay, so that's the primary, let's say, description for mechanics. Although there are topics that's more on topics like for example the moment of inertia or the mass moment of inertia. But the main thing right here is the forces and its body response due to the applied force. Now, in your statics, let's say we have a beam right here, and it's simply supported, and it is subjected to flexural loads, transverse loads. And for now, let's assume that this body is a rigid body. Okay, so because of this external force, what is developed, or the response of the body, would be the support reactions. And also there's a response as well in terms of the internal force, right? That's inside the body. What's happening inside the body, or what's the force that this body is experiencing? Let's write it here: internal force. Okay, so again, we have a rigid body here, and once the external force is applied, the response is the support reactions and the internal forces. And I call this a static response. Okay, and if we're just dealing with the static response, that's the concern of engineering statics. Engineering statics. That's ENSC, I guess, 104. Now, another response of a body when a force is applied to it is, for example, we have this object right here. Then let's consider this a point 1. Right? This is point 1. And once you apply a force, then another response would be the translation or rotation, right? So meaning that it will have motion, or let's say displacement. This is delta S for the displacement. Because of that force, this object displaced. Now I call this a motion response or dynamic response. And if we're talking about the mechanics about this motion response of a rigid body, again, let's assume this is a rigid body, and that's a concern of engineering dynamics, or ENSC 105. Now, another response to forces, for example, I have a bar and I subject this to axial loads, tensile. But then for now, this body is no longer rigid. Let's say this is deformable body. But actually, it's more like, I think it's more precise to say deformable solids rather than just body. Now, call this deformation response. And if we are talking about the deformation response, that's the concern of strength of materials or mechanics of deformable solids or bodies, materials. Okay, so because of this force, the response would be it can elongate, right? So if you're trying to pull this bar apart, then one tendency would be it will elongate, it will deform. This is your original length, and you have this deformation. Okay, so deformation response, that's a concern of strength of materials. Okay, now you would notice that this is this talks about solid bodies. Now for fluids, if if the body concerned is fluids, then that's gonna be subject of fluid mechanics. So that could be the static response or the static, let's say static conditions, or it could be in dynamic conditions if we're talking about the deformations, although probably not much about this. As long as the body that we're talking about is a fluid, then that's going to be the subject of fluid mechanics. So therefore, we can write that fluid mechanics is the study of forces and fluid responses, its properties. I think I should write it this way. Let me rewrite it. Okay, so fluid mechanics is the study of fluids study of fluids, its properties, forces involved, right? Forces involved, whether it is in static, whether it is in static or dynamic conditions, as well as the governing laws and principles. Right, so that's going to be my definition of fluid mechanics. Now for the governing laws, it will always be the conservation of mass, the conservation of energy, and the conservation of momentum. Okay, so this is the fundamental governing laws in the study of mechanics. Okay, so now let's go on to the concept of continuum. Right? So it's like the continuum assumption. Okay, so it must be understood that when we're dealing with mechanics, it could be solid mechanics or fluid mechanics, so it is usually, this assumption is usually used in the analysis or the problem solving of problems. Okay, so the continuum assumption, it is a view of matter where matter is composed of of infinitesimal elements. Infinitesimal elements. Okay, so again, this is just a view of matter. That a matter is comprises of infinitesimal elements. That's called continuum, right? So it's actually a continuum, or sometimes I refer to that as a differential volume. Okay, so it's like you can compare this one, continuum versus quantum, right? Quantum, or let's say atomic. Okay, so this one is a view of matter, continuum view of matter, that no matter how much you divide a matter, it's still the same thing. I mean, it has the same composition. Okay, whereas this one, the quantum, if you divide, or if you try to look at the smallest possible particle, that would be a quantum, or that would be in the quantum view of matter, or we say that's about the atomic level or molecular level, right? When I say water, let's say we have water. Now, if you try to look at this in terms of the quantum view, then we get H2O, right? And if you go deeper, then that's about electrons or protons or whatever. But here, it's still gonna be water at its smallest level. And so here, if it is atoms or particles, this one, it's continuum, or that's what I've said, infinitesimal elements. Now, I like to use these words sometimes because this is calculus, right? Before the concept of limits, it's all about infinitesimal elements. Okay, so the concept of this infinitesimal elements is that, for example, I have a steel, right? Let's say I have a steel. Well, let me draw it in one view, right? So let's say this is X, this is Y, right? So if this is steel, then and I try to cut it in half, divide it in two, then my question is, what is the composition of this half? Is it still steel? Or let's just say cheese, right? So let's just say cheese. Now, if this cheese I cut in half, then what is the composition of this half? Of course, it's still cheese, right? Now, I cut this half into half. So I cut 1/4 cut. Now, what is the composition of this 1/4 cut? It is still cheese, right? Now, if I cut it here and then I cut it I cut it half every time, then what you get is the smallest element, right? That's actually infinitely small, and you still get a cheese. You don't get the molecular structure of this cheese. Now, that's the view of the continuum. Okay, so therefore, if this is our body, we can view it something like this, right? It's composed of cubes, or depending upon your let's say coordinate systems. Now, for this one, if I apply force right here, then it just means that it has every cube has this. And let's say we have these forces for every cubes, and what we get is an average value, right? And that's why sometimes you have encountered the term, example, pressure at a point, or stress at the point, right? It's just simply because of that this infinitesimal object is actually it's like a point. If you shrink it down to 0, it's like a point actually. So this point, if we zoom in this point, it's like this. And so now the question is why does it have to be a cube? Again, that would depend upon your coordinate systems. Now the question is, why do we need to make coordinates? Now that's because the reason is so that we can locate the points, we can find the motion or the translation of the motion of the points and things like that. Okay, so now let's move on to this graph. In our lecture handouts, there's a graph that's on this vertical axis. We have the delta m over delta v. Then right here along the x-axis we have the delta v, the change in volume, or the, let's say, the differential volume, right? And then this one, the mass over volume, that's actually density. Now if we consider here, let's say we have a container, and then let's say this container is filled with water, right? Now if we consider a large differential volume, meaning maybe something like this, if you consider this large differential volume, looking at the molecular view or atomic view of matter, we know that it's all about the molecules, right? Meaning that there's in this, let's say in this window, or in this volume, or in this window, there's a lot of molecules that's entering and let's say entering and exiting this window, right? So because of that, the density in this window is almost constant. I mean, the variation would be not significant. Therefore, we'll get a almost a constant, right? Almost a constant density. But then, if we try to shrink the window, let's say we'll consider a small window, then we would notice, or we can have significant, let's say, observation on the changes or fluctuations in the density, right? So let's say we have something like this, and now if we shrink it some more, then of course we can have, or we can observe fluctuations, larger fluctuations in the density in that window, right? So therefore, the validity of this continuum assumption is only up to here, right? So let's say continuum assumption. All right. Now, if a fluid mechanics problem requires that we have to take into account the molecular structure, then it must be analyzed using a model that correctly accounts for the molecular structure of the fluids. Okay, so that's the continuum assumption. Okay, now let's discuss what is a fluid. In the world of continuum mechanics, we only have two types of bodies, or two types of matter, and that's solids and fluids, right? And in fluids we have liquids and gases. Okay, so this is our atomic view of matter. We have solids, liquid, and gas. But in continuum view of matter, we only have liquids and we only have fluids and solids. And we say fluids that that encompass the liquids and the gases. Right. So, what do you think is the characteristic of liquids and gases? Now we can observe that basically they are substances that flow, that flows. However, this is just a basic definition. Basic description, because if you say just substances that flows, then what about, the question is, what about the granular solids? Granular solids, they also exhibits flowability characteristics. Right, so therefore we need a precise definition of what a fluid is. Okay, so for the precise definition, we can say that a fluid is a substance that deforms continuously under the action of shear stress. Right. Okay, so again, a fluid is a substance that deforms continuously under the action of shear stress. Okay, so recall that the shear stress is a force distribution perpendicular to the area, right? So let's say this is our infinitesimal element, and we have this force that's parallel to this area. That's what we call shear stress. This one is shear force, but if it's the shear force divided by the area, then that's going to be the shear stress. Then another one, if you recall, is the axial stress. Now, axial stress is basically a force that's perpendicular to the cross-sectional area concerned. Okay, so the difference between a fluid and a solid is that if we apply shear force on a solid, what we get is a finite deformation. Right, so let me draw it here in 3D. Right. Then let's say this is x, this is our y, and then this is our z. Or x, y, and z. Okay, so if we try to look at the xy plane, then this is our element. Let's say this one is solid and this one is fluid. A solid infinitesimal element and then a fluid infinitesimal element. And if we apply a force, let's apply a force on both of these infinitesimal elements. Right. Okay, so when you apply a force in a solid, what you get is a deformation, right? So you will have, let's say we have a fixed bottom. Okay, this has a fixed bottom, and then this one too has a fixed bottom. Okay, so if you apply a force, then because it is restrained at the bottom, then what you get is a translation at the top portion on this top layer. All right, so once you remove this force, it will go back to its original shape, or slightly go back to its original shape, right? Depending upon if the yield strength is reached. Okay, so for solids we have finite deformation. But for fluids, once you apply force, you get actually a deformation that's continuous. So it will deform continuously, right? Of course, this is just a simplification, but and again, please understand that we're talking about the infinitesimal elements, differential volumes, right? So actually, there's no way that you can have a cube. There's no way that you can have a cube fluids, right? But again, we are talking about infinitesimal levels, right? So we can have this, let's say, simplifications. We have, we can say here, if you apply for fluids, if you apply shear force, you have a continuous deformations. Okay, so recall that in generalized Hooke's law, we have that stress is directly proportional to strain, right? This one is force over area, and then this one is the something like a percentage of the deformation divided by the, let me write it here, just basically deformation divided by the original length, right? Whereas this one is force over area, right? So this is a generalized Hooke's law. It's actually generalized because the original Hooke's law is all about force and deformation, not force over area and not deformation of original length. Okay, so it's just force over force versus deformation. That's the Hooke's law. Okay, so if we change this this proportionality symbol, we get E and then the strain, right? So we have the axial stress is directly proportional to the axial strain by this amount, by this elastic modulus. And this one, this stress, this kind of stress is axial stress. Of course, this one would be axial strain, but we're talking about shear here. Okay, so there is also a counterpart of this equation, but with regard to shear. So we have shear stress is equal to or is directly proportional to the shear strain, right? So this one is shear strain, then this one is shear stress, then this one is the modulus of elasticity, right? So that's the equation for solids. Now for fluids, since it continuously deforms, then it means that the shear stress is directly proportional to the rate of shear strain. So that's a rate per unit. That's per unit time. Okay, so now let's define what is this this rate of shear strain. Alright, so let's again draw our infinitesimal element. By the way, I don't have much time left, so I'll continue our discussion in the next video.